there's possibly some message. So I'm going to talk about formalizing undergraduate mathematics and why this seems to be a ridiculously unfashionable thing to do, and yet why I think it's so supremely important. So thank you very much for the invitation. And during the talk, I'm going to say something about, my former life as a research mathematician, and how my research mathematician friends, what they think about what I'm doing now. And then I'm going to talk about formalizing undergraduate mathematics. I suspect that the audience will be rather sympathetic to the idea of formalizing undergraduate mathematics, but not everybody is. And then I'm going to talk about formalizing undergraduate mathematics, or I'm going to give an overview of what's been happening in the Lean Theorem Prover. The Lean Theorem Prover has a library called MathLib, which is Lean's maths library, which contains a lot of undergraduate mathematics right now. So there's an overview of where we're going. And so briefly, just so you understand how this all came about, for 20 years, I was just a normal number theorist. I did research in something called the Langlands program, which is a part of algebraic number theory, a very significant part of algebraic number theory, all taken very seriously by serious research mathematicians. And then in 2017, as Christoph said, I got interested in formal proof verification, and I got interested in it for two reasons. The first reason was pedagogical, because I'm very interested in teaching. Both my parents were teachers, and I thought that I'm interested in using new technology to teach. So I thought that learning about these proof verification systems might be quite interesting. And also, maybe I should say that there's something wrong, in my opinion, with MSc projects in pure mathematics, at least at my university. And talking to other people is a similar story at many other places. What you tend to do with an MSc project, MSc students are not ready to do original research in most cases. And so you just have to give them something that's very well understood and tell them, you give them the book and you tell them to copy it out. It's a terrible thing. You say, well, you want to learn about this part of number theory. Well, here's a very respectable book by a very respected author. Why don't you copy out chapters 1 to 4 in your own words, and that can be your master's project. And I was slowly getting sick of such projects. I've been doing them for 20 years. Very few students had done anything original, and it was really quite boring supervising them. So there were pedagogical reasons as to why I thought that these theorem provers might be useful. But also, independent of that, I was having some kind of midlife crisis, and I was slightly worried about the state of modern number theory. It's something which we'll get to a little bit later. But for those two independent reasons, I started dabbling in formal proof verification systems, in particular, the Lean Theorem Prover. So none of my colleagues had ever heard of the Lean Theorem Prover. I mean, the Lean Theorem Prover is supposed to be proving mathematical theorems, but my colleagues, it's also their job to prove mathematical theorems, and none of them have ever heard of it, because that's how things are in a modern maths department. Essentially, 0% of people are using this kind of technology, ITPs and ATPs. Of course, there are some exceptions, but most people are not using it. And in 2018, I decided, I mean, the UK is kind of a small place, and number theory in the UK is a small group of people. We all know each other, and so I thought, this would make an interesting talk. So in 2018, I went on a UK tour, basically, attempting to tell my friends that we should all start using theorem provers. So let me briefly go through my failed attempt to convince mathematicians to use theorem provers, and then we'll get onto the order of the day. So here's a page from the Annals of Mathematics website. It's the most prestigious pure mathematics journal. I mean, it published the proof of Fermat's last theorem, for example, but it's also published many other serious mathematical results. It's a generalist pure mathematics journal. And here's something from 2004, a paper full of insights that proves, certain moduli spaces are quasi-projective. And then here's another paper from the Annals of Mathematics from 2006, that proves that not all moduli spaces are quasi-projective. And in the abstract of this second paper even remarks that the main theorem of the second paper contradicts the main theorem of the first paper. And both of these papers are published in the Annals of Mathematics. And so that I find that funny, because now, of course, if you believe everything in the Annals of Mathematics, you can now prove the Riemann hypothesis, because, I mean, you can prove naught equals 1, right? So you prove naught equals 1, you deduce the Riemann hypothesis. You could send that paper to the Annals of Mathematics, and they probably won't accept it. They definitely won't accept it, but they've never retracted. I mean, one of these papers must be wrong. These two papers between them, one proves the opposite of the other one. No retraction of either paper was published. And it turns out the incorrect paper is really useful. Both papers are useful, but the incorrect paper in particular has got some profound ideas. And I've talked to people who've said that their research has been really inspired by the ideas in the incorrect paper. But the Annals is somehow too embarrassed to say it published an incorrect paper. So we're left with that situation. And of course, it's funny. And that's the end of the story. Yes, isn't it funny? The Annals published two papers which together give you a contradiction. And of course, if you're in with the in crowd, you know which paper is correct, right? And you know where the mistake is in the other paper. For example, quite a good way of finding out what's going on is by reading the reviews of these papers on a site called Math Reviews, run by the American Math Society. But you have to pay to access that site. So if you're lucky enough to be at a research university which pays for access to Math Reviews, you can find out which paper is wrong. But of course, just because the paper's wrong doesn't mean it's worthless. That wrong paper's got lots of great ideas in. But somehow we're not very good at picking up the pieces after ourselves. There's no explanation of what's going on that's kind of publicly available, which in some sense I think is disgraceful. Because if you're from a developing country and you're trying to learn some algebraic geometry, you don't have access to all the information here. And mathematicians they're not too bothered about that. So I got a bit upset by this and various other things. And that was what started me off, really. In 2018, I put together a bad mathematics talk, kind of, sort of shining a light on some poor research practices that are going on within my own community. And I emailed a few friends, and within a few months, I found myself going around the UK, giving this bad mathematics talk at colloquiums at universities across the UK, and I was highlighting proofs with holes and proofs which everyone was using, which were unpublished. Proofs with holes that could be patched, proofs with holes that couldn't be patched, and the general mess that mathematics is in if you're a formalist like me. And I went and told a lot of basically this was my announcement in some sense that I was going to be starting doing something else now. And I went around the UK giving this talk and saying to people that, they should basically get off the sinking ship, quite an extreme viewpoint. And this talk went down like a lead balloon, basically. This talk went down extremely badly. So what I discovered first was that many people didn't recognize my objections. They said, yes, of course, some things are wrong, but most of the important things are fine. And the experts know exactly what's true. So that was a very common objection to my point of view. And another one said that it didn't matter because even if papers were wrong, I mean, we've seen an example, even if a paper is wrong, there might still be good ideas in it. So, and the fact that, I don't know. Apparently, it doesn't matter that we've published incorrect theorems. And other people said that actually I was just being very naive, and which I can quite believe because I'm not really a historian of mathematics. But apparently, mathematics has always been like this, where there have been half understood things, and people are clearly having important ideas, but they're not getting written down completely correctly, and then things kind of get sorted out later. So in fact, I'm just looking at a random point in history where there are problems in the literature, but there are always problems in the literature, and the important problems get sorted out later because the experts know what's going on. So this was the general response from serious mathematicians. And so I did start reading around, and I found these two, here are some very elegant expositions of both sides of the argument. Jaffa and Quinn argued that some mathematics shouldn't be regarded as, you know, I mean, they wanted to distinguish between mathematics which convinced the reader and mathematics which had been absolutely checked from the axioms. And then Thurston wrote a huge retort to this. And Thurston, of course, has a Fields Medal. You know, Jaffa and Quinn, you know, Quinn's interested in education, and maybe Jaffa is primarily a physicist, but Thurston, who has a Fields Medal in mathematics, he wrote a retort to this argument and said that it was extremely important that we let people make errors, because somehow the thought process is the most important thing. So, you know, it's an interesting and lively debate that one can have. But after a while, I kind of got sick of having it, because I was clear that we could do better, and yet it was extremely difficult to try and persuade people, to try and persuade my colleagues, my research mathematics colleagues, that we could do better. So that was my experience with talking to research mathematicians about the state of mathematics. So I raised these talking points to them, and they will happily go down the pub and talk about them, but then nothing really happens at the end of it. So, for example, mathematics has now got too big for people to understand. There's no one person, I believe, there's no one person who fully understands all of the details of the full proof of Fermat's last theorem, which I think is interesting. Mathematics has just got bigger, you know, than the human brain. But on the other hand, it's absolutely clear mathematics is modular, right? You prove a theorem, and then someone else can use the theorem without understanding what the proof is, and use the theorem to prove something else. And so because of the nature of this, it's absolutely, undoubtedly, you know, no one is suggesting that Fermat's last theorem is not completely rigorously proved. And yet nobody understands it. There's no somehow one document that contains all the details. I mean, that document would be very large. This is a very contentious, mathematicians don't particularly like talking about the ABC conjecture, but a former Princeton professor, now in Japan, Mochizuki, announced a proof of the ABC conjecture, and there's a fierce debate in the community as to whether this proof is correct. But a recent development is this proof is now going to be published. And of course, this is difficult because we were always arguing, you know, people who were against this proof were saying, well, it hasn't been published yet, and it's 6 years old. And so, you know, you can see that something's going on, but now it's going to be published. And the community does not all believe this proof, and yet it's going to be published anyway. And on the other hand, everybody believes the classification of finite simple groups, even though essentially nobody, you know, very few people alive have read it, and it's still unpublished. I mean, people are working on getting this proof into the literature, but it was announced 40 years ago, and it caused a massive exodus of the area, and yet still not properly written down. So it's a funny thing. And then there's this thing that personally annoys me a great deal. You get experts saying, I know how to prove, you know, here's a proof of theorem X. I can actually prove theorem X primed, which is stronger, but details will be forthcoming, and then they don't appear. So that's, you know, a personal pet peeve. And then what else have we got? The system's worked for thousands of years, why change it? You see, and that's exactly, I mean, that's absolutely true. The system has worked for thousands of years. We've made huge progress. Why change it now? And then, of course, there's the argument about whether computers will save us all. Should we be digitizing mathematics? And some people think that it's clearly the future. And some people also think it's pointless. Some people think both, right? That can really happen. They certainly don't want to be digitizing mathematics, but they can kind of see that at some point something will happen. So the last quote is a quote. This is Brian Birch said this. Birch and Swinnerton and Dyer had this famous conjecture about elliptic curves. One of the sort of, you know, it's one of the clay millennium problems. And Swinnerton and Dyer died around a year ago. And I went to his memorial, and I met Brian Birch there. And I told Brian that I was switching from number theory into computer mathematics. And this was his first question: can they tell us anything new? And by new, he doesn't just mean a theorem that no one's ever proved before. He means a theorem that humans are interested in and they can't solve, and then computers can come and solve it. So we're nowhere near that yet. But on the other hand, it's kind of not inconceivable that this will happen one day. But this is a big problem to get research mathematicians involved. Computers can't tell us anything new right now. And so why should they be interested right now? You know, they'll get interested in 10 years' time when things are looking better. So that's what I was doing in 2018, trying to convince mathematicians very unsuccessfully that there was a problem with their area. But independently, so it's not clear whether there's a problem to many people, and it's certainly not clear if formalization is the solution to that problem. So that's the end of the first part of what I wanted to say. And now I want to talk about my work with students. So whilst I was, you know, getting interested in theorem provers and in the lean theorem prover in particular, because I had these pedagogical interests, I'd started working with undergraduates, and collaborating with undergraduates is quite interesting. It's very different to collaborating with researchers, because I don't know, they were just a lot more random, but some of them have, you know, it's just interesting working as an equal with undergraduates. It's something I'd certainly never done before as a professional number theorist. And we started formalizing undergraduate level mathematics just for fun. And I was, of course, carefully watching them to see if they were learning it in a different way, using a system called Lean. I see there's several Lean talks later on this week. In fact, there'll be one talk about Lean's maths library, which I'll say something about later. And I was lucky because this all started for me 3 years ago in 2017, just after Lean's maths library had split off from core Lean and had become an independent library. And there was just enough in there for it to be usable. For example, it had the real numbers, which is a really good start if you're a mathematician. The real numbers are a pain to make, but they were there, and theorems about the real numbers were there. There was basic ability to do calculations. There was a huge theory of finite sets, which is, Lean uses dependent type theory, and finiteness is problematic probably in any, you see, I say problematic. Humans understand, especially human mathematicians who don't use computers, they understand finiteness very, very well, very clearly and intuitively. And they find it quite surprising that when you start formalizing things, finiteness becomes a very thorny issue. And statements like, there's no injection from a set of size 10 to a set of size 9. The fact that this might need a proof, and the fact that mathematicians might not really be equipped to give such a proof, could be problematic. But we had a very, very solid theory of finiteness, finite sets, finite subsets, written by Mario Carnero for the main part. And there was also a lot of topology written by Johannes Herzl. These two people had really driven MathLib development in its early years. But the reason it was just perfect was things like the complex numbers were not there. The real numbers were there, the complex numbers were not there, but a complex number is just a pair of real numbers. So this is a very basic exercise that one could do. One could define the complex numbers and start proving basic things about the complex numbers. And this is the kind of stuff that, you know, undergraduates can do. And so I started showing this stuff to undergraduates and doing various bits of mathematics from our undergraduate curriculum. And the undergraduates were far more receptive to the idea of formalizing mathematics in a theorem prover, far more receptive than the staff, because they thought it was kind of new and cool and interesting. And of course, some of the staff members don't use computers at all. They use computers for email and, you know, and for Zoom, but they're not using computers in their research. Whereas undergraduates are using computers for everything. You know, they're using computers for their entertainment. They've been brought up playing games on computers, and they've been learning mathematics on computers. You see, I didn't learn mathematics using computers. I learned mathematics from books. They've been learning mathematics from YouTube. Computers and mathematics are much more seriously intertwined in the head of an undergraduate. They're watching YouTube channels which are teaching them undergraduate mathematics, and they're, you know, downloading lecture notes from the internet. So they're somehow, for them, computers are much more normal. And I found that, you know, they were interested. And so I started a club, a little formalizing club on Thursday evenings at Imperial College London called the Xena Project. And I just left it at that. And people would come along and we would just do mathematics, and we would learn how to use Lean, which is this dependent type theory, theorem proving thing, written by Microsoft, I should say, Microsoft Research. And things were good. Things were great. Weekly Thursday meetings. They used to be at Imperial. They now moved to Discord, which is a thing that young people use. It's a thing where young people get together and play computer games together, except some young people get together and do lean together on my Discord server. And undergraduate mathematics, now undergraduate mathematicians from all over the world are welcome, and we typically meet Thursday evenings. And that's how I got interested in formalizing undergraduate mathematics. So how did it start? We started by formalizing the stuff I was teaching them. I was teaching the first years a basic introduction to proof course. And I thought, well, this is going to be easy because I know this stuff back to front. And actually, some of it turned out to be essentially impossible because sine is not opposite over hypotenuse. Sine at university is defined to be an infinite sum. And although we had the theory of real numbers, we didn't have a good theory of convergent infinite sums. And we certainly didn't have differentiation. We couldn't prove that to define sine, we were going to have to prove that a series converged, and to prove that its derivative was cos, we were going to have to prove that that you could differentiate a power series term-wise. And these are quite fiddly proofs, and they were certainly not in lean at that time. So the earlier stuff I was doing with sines and cosines and e to the I theta was extremely difficult to formalize in lean. But then the more abstract stuff I do later, I start talking about sets and functions and equivalence relations, the later problem sheets. And this was really, really easy to formalize in lean because it didn't rely on a huge theory of, of the real numbers in calculus. This was all very, very much first principles stuff. And then students, a student specifically said to me, you gave lectures on equivalence relations. I didn't understand them. I then went and formalized them in lean, and now I understand them. And students were saying things like this to me, and I was thinking, there's got to be something here, really. But one thing I learned very quickly was that actually formalizing mathematics in the order that we teach it to the undergraduates is a lousy idea. I mean, I can imagine there are people watching this talk and laughing now. This is something that I only learned recently, but this is presumably a completely standard observation. One shouldn't formalize mathematics in the order it's taught, because somehow people arrive at university with an intrinsic understanding of what the real numbers is and what the real numbers does, but actually building that stuff from scratch takes a lot of work. Whereas on the other hand, defining a group is very, very easy. You see, so these are examples of things that it took well over a year to get to in lean. But on the other hand, any mathematician will tell you that this is first year stuff, right? That's how undergraduate mathematics is characterized by mathematicians. There's first year stuff, there's second year stuff, and there's third year stuff. So we had trouble doing this first year stuff. But on the other hand, algebra, lean already had rings, because a ring, you see, computer science can just knock up the definition of a ring because it's just a bunch of axioms. Lean had rings, and lean had equivalence relations. And this is all you need to do localization of rings. And localization of rings, if you ask a mathematician, well, this is abstract algebra, so it's third year stuff. But I'm looking at this stuff thinking, well, equivalence relations were easy, and rings look pretty easy. So localization of rings should be easy. So why don't I see if I can teach, quotes, third year stuff to first years? And there was a guy called Kenny Lau, who was a first year and who was very interested and clearly quite able. And so I said, well, here's a book by Tier and McDonald. Why don't you go ahead and formalize some, third year mathematics, you first year? And he just did it effortlessly. He learned how to use lean, and 2 months later, he was formalizing, quotes, third year mathematics in the lean theorem prover and getting it accepted by Lean's maths library, MathLib. And then there was another guy, another student who was clearly very interested, Chris Hughes, and he started on the group theory course. And the group theory course is ferociously difficult because it has all this finite stuff. The first year group theory course is basically the theory of finite groups, and there's all these counting. We're constantly counting, and you split up a set into a bunch of subsets, and it's completely obvious that the size of the set is the sum of the size of the subsets. But to do this formally can be quite difficult. And Chris started making progress. I remember the day that Chris told us he'd formalized Lagrange's theorem in lean, and Kenny was genuinely impressed. He was shocked and impressed. And Kenny was doing, quotes, third year stuff. And then I saw him being impressed that Chris had done, quotes, first year stuff. But then I realized that actually this first year stuff was hard because it involved finiteness. And I realized that I'd made a team, right? We have a team. There's me and Kenny and Chris, 2 first year undergraduates and this number theory professor, are now talking at the same level about formalizing mathematics. And I said, let's do some, let's do some MSc stuff. Let's formalize the theory of schemes, because why not? So we started work on the theory of schemes, me and these two undergraduates, and it took us about 3 months, right? We were just working, I was doing other things. I was writing a paper, this was when it was still part of my, leisure time. As far as I was concerned, this is leisure time. This is like playing computer games, right? Formalizing schemes indeed is like playing Zelda on our Wii. So it took us about 3 months working on and off, but we just knocked it off. We ran into problems, we solved the problems, we learned how the theory worked, and then we finished, and we had a theory of schemes, and we'd made several poor design decisions, all but one of which we'd fixed. But there was still one disastrous design decision that made using them very complicated. And at that time, I still wasn't entirely clear how to get around it. So I started asking around on the Lean chat, or just asking people that knew these things, how were schemes done in the other theorem provers? Because they're 50 years old and they're standard MSc material. And it turns out that there weren't any schemes in the other theorem provers. And the fact that me and two first-year undergraduates had formalized the theory of schemes meant that in theory, we could probably write a paper about schemes now. And that paper is slowly but surely being written, although it's still not done. And the work is now 2 years old, which is not a good sign. So this was when it occurred to me that actually this whole area was completely different to how I'd imagined it would be. Because I just thought that somebody would do schemes for fun, and there they would be. Schemes would be done in Coq and in Isabelle Hall, and I was going to look at how they were done in these other systems and learn how to do them. But they just weren't there. And then I started digging even more, and it turned out that not only is there standard MSc stuff missing, there's standard undergraduate stuff missing. I teach my third years about number fields. I teach them that I prove that the class group of a number field is finite. So who first knew that class groups of number fields were finite? I mean, this stuff goes back hundreds of years. Gauss figured out what the class group of an imaginary quadratic field was. And they're taught to the third year undergraduates at my university. And this is the big theorem about class groups. Class groups are always finite. And you can say, well, what's the proof? Which of the systems can prove that? And the shocking answer, at least when I was looking at this 6 months ago, is that no prover can currently state that theorem. Because to state the theorem, you need to know what the class group of a number field is. So this upset me, because now I realized that I couldn't possibly say to these research mathematicians, look, they already know an undergraduate. I somehow just assumed that the basic stuff was all there. But in fact, no research mathematician takes undergraduates seriously, right? This is somehow the problem. Undergraduates can't tell you anything new because they're undergraduates, right? They have to somehow, once they start doing their PhD, is at that point they start asking interesting questions. But undergraduates will, an undergraduate will never ask you an interesting question because they're dealing with mathematics, which is 50, 100 more years old. And it's stuff that is extremely well understood. Our job is to teach the undergraduates. Our job is to get the undergraduates to where we were like 100 years ago in some areas. Certainly things like analysis and abstract algebra. We're taking them to the forefront of the 20th century in undergraduates, in the undergraduates. So this struck me as a problem, right? If no research mathematician can see undergraduate mathematics, then we're going to have to make it. So computer proof checkers, they've been around for a long time, 50 years or so. There's some examples. ITPs are what I'm particularly talking about. Coq, Lean, Agda, Isabelle Hall. Coq is 31 years old, an extremely respectable prover. And there's many, many small projects written in these systems. They're probably incompatible. If you tried to use 5 small projects at once, you would have problems because you might find that these 5 small projects use 5 different definitions of the natural numbers. But there's also some seriously non-trivial mathematics done in these computer proof checkers, but no systematic development of an undergraduate degree. And I just realized that somehow almost by accident, this is what we were doing at Imperial College. We were beginning to build an undergraduate mathematics degree. We were beginning to turn MathLib, Lean's maths library, into an undergraduate, into an object that knew an undergraduate mathematical degree. And it struck me as a really good idea. I mean, why not just make one? So I started to try and work out why one hadn't been made and what were the obstructions to making one. And just generally, these are the questions. So maybe we should get research mathematicians to make an undergraduate mathematics degree. So research mathematicians, you talk to them, they are accepting of the fact that one day there'll be some revolution and this software will change things, but we're nowhere near that revolution at this point. And to me, it's self-evident that starting, why don't we start teaching computers the way we teach students, and at least let's get an undergraduate degree into one of these systems, one coherent place where you can import one thing and have an undergraduate degree. But the serious research mathematicians aren't interested in doing that because it's boring old undergraduate mathematics. And the serious research mathematicians control where the funding goes, right? So I can't apply for funding to formalize undergraduate mathematics. So I have got funding for formalizing in the past, but it's for funding research mathematics. And because they can kind of understand that there's some, research mathematics is kind of interesting. But undergraduate mathematics, the mathematicians aren't going to fund it, and the research mathematicians aren't going to do it. And computer scientists, they're not really interested in formalizing undergraduate mathematics. Computer scientists take on big projects, right? They formalize the Feit-Thompson theorem. This is an extremely long and difficult theorem about finite groups. They formalized the proof of the Feit-Thompson theorem, and Thompson got the Fields Medal for this. So the computer scientists are claiming that they're formalizing Fields Medal winning work. You see, unfortunately, they're formalizing Fields Medal winning work in the theory of finite groups. And when the classification of finite simple groups was announced, the experts just exited the area. The area was killed by the classification of finite simple groups. And this, I think, is one of the reasons why it's never been written up properly. So they formalized a brilliant theorem, an extremely deep theorem in a completely dead area. And they even did it constructively. They didn't use the law of the excluded middle. And mathematicians are just looking at this work and thinking, we don't really care. We care about fancy modern mathematics, not this 50-year-old stuff. So somehow this didn't turn mathematicians' heads. But of course, these computer scientists, they needed a whole bunch of undergraduate group theory and number theory and representation theory. So they formalized just the parts that they needed as part of their project. There's somehow not an attempt to develop a theory. Now, why don't we develop basic undergraduate number theory and basic undergraduate representation theory just as a standalone thing, and basic undergraduate everything? So these things were done as part of a much bigger proof, and they just did the things that they needed and then moved on from there. You see, because that's the thing, the goal was to formalize this difficult proof rather than to formalize, a body of useful mathematics. So this is my impression. These ITP users, mostly computer scientists, they seem to be focused on proving theorems. I once made a definition in one of these things. I defined a perfectoid space together with Johan Kommerlin and Patrick Masso. And a lot of people said to us, what's the point of formalizing a definition? Anyone can formalize a definition. You should be formalizing theorems. But actually, it's the definitions which are missing, right? We can't formalize the proof that class groups are finite because we don't have class groups. So these people formalize the things they need to prove the theorem. And computer scientists, when you say, let's formalize undergraduate mathematics, they say, where are the publications? How am I going to get a publication if I formalize a body of undergraduate mathematics? What would be the point somehow? It's all known anyway, right? And it's probably all been done. I would imagine that most of undergraduate mathematics has been done in one theorem prover or another. Somewhere you'll find most of the stuff in an undergraduate degree, but you won't find it all together. So mathematicians need this material. I'm a number theorist, and number theory is an extremely old subject. And in fact, it turns out that to do modern number theory, you need all of a pure mathematics undergraduate degree, basically, not just the number theory courses. You need all the courses. So mathematicians aren't doing it. Computer scientists aren't doing it. AI people would love it. AI people, it seems to me, are just missing databases. They need a big database of stuff to train their AIs, but they can't even train AIs on undergraduate mathematics because the undergraduate mathematics that is there, it's spread over about 5 systems, and this makes it kind of useless. And there's no funding available, as I say, not for formalizing undergraduate mathematics. And so if you talk to Christian Szegedy, who's also speaking this week, Christian Szegedy just wants to train computers to read human literature. But I think that this is an extremely difficult problem. And I've also seen human literature that contains mistakes. And so Christian is optimistic and I'm pessimistic about getting computers to read books. But of course we shall see. But I want it now. I can't wait until computers can learn to read human literature. And so how about we just use more undergraduates? Because they type up their lecture notes in LaTeX. How about we just train undergraduates to start typing up their lecture notes in a theorem prover instead? Because some undergraduates are bored at my university because they know the material back to front. They're extremely talented and they just want to learn new stuff, right? They want to learn new stuff. Why don't they learn how to formalize? So now let me talk about, finally, the last third of this talk, let me talk about formalizing undergraduate mathematics in Lean. And unfortunately, I found that it's not as easy as just telling undergraduates to type up their lecture notes. Because as I mentioned earlier, it's best to do things in a different order. For example, we teach the first years a basic integral, a basic theory of integration. We teach them the Riemann integral is defined as a certain kind of limit. And I said, why don't we put the Riemann integral in Lean? That would be cool. And everyone said, no, the people that knew what they were talking about. Because what you should do is you should prove a far more general theory of integration first. You should define the Bochner integral, which is certainly not defined to our undergraduates. And it takes values in, not the real numbers, it's taking values in topological vector spaces, which are also things that we say very little about to the undergraduates. So you develop a very general theory of integration, taking values in general topological vector spaces. And then you start specializing. You do a whole bunch of measure theory, third year stuff. You do a whole bunch of topological vector spaces, third year stuff. You do, the Bochner integral, MSc stuff, and then you deduce the Lebesgue integral, third year stuff. And then maybe we could talk about, and then you start asking what the point of doing the Riemann integral is, because now we've got the Lebesgue integral. So the naive idea of just getting the first years to type in their first year syllabus into Lean doesn't work, at least in analysis, because, undergraduates don't know the Bochner integral, and most of them don't know what a topological vector space is. But with algebra, it does seem that actually with algebra, you can just start building it the way we teach it. And so I really pushed my undergraduates to develop algebra. And as a consequence, not all of this was done by Imperial undergraduates, for sure. A lot of it was done by other people, but there was always this push, like we need to do this. We need to do third year undergraduate algebra. We need to get it done somehow. So can the experts please tell us how to formalize modules? So rings were there when I started. And then, these special kinds of rings that we teach the second years, principal ideal domains, unique factorization domains, Euclidean domains, those are all there now. And then modules over a ring, that's third year stuff. And finiteness conditions on rings and modules. I was pushing for these things to be in there, and other people tended to do them. Often experts, when it comes to definitions, you need an expert. But when it comes to theorems, undergraduates can happily prove theorems. And all this work is unpublishable because it's completely standard mathematical material written by people for fun because they were just developing a mathematics library. But it's looking very similar to the kind of things that we're teaching our second and third year undergraduates now. And it's not been done because we're trying to prove the big theorem or a big theorem. It's just been done because one of the jobs of Lean's mathematics library is to be, a one-stop shop, a go-to place for a lot of undergraduate mathematics. And do you know what? Doing it taught us a huge amount. Even the people that were Lean experts when we started, the computer science people that knew a lot about dependent type theory, it taught us a huge amount about how to formalize mathematics in Lean. So there's this thing about implementation versus specification. A number theory knows what a group is, but a computer scientist has got to figure out exactly how to store groups in a theorem prover. And we all know what subgroups are. Mathematicians know what a subgroup is, but the computer scientists have got to decide how to store the concept of a subgroup in a theorem prover. So we all knew that we needed groups, subgroups. We all knew that we needed polynomials. We needed modules over a ring. And the first implementation of every single one of those things was wrong. We implemented many things right, but all of those four things we got wrong. And then we tried to use them. They were difficult to use. And then we started again. And for example, an Imperial undergraduate did do subgroups. The current theory of subgroups in Maths Library was written by Jason Kexing Yang. He rewrote the theory of subgroups. the way that we discovered was the correct way. And Amelia Livingston rewrote the theory of localization the correct way. So we made mistakes, but we're good at going back and fixing things up. Subgroups are still, the old way of doing subgroups is still a little bit in the library, but we're trying to, it's a current project of mine to get rid of it. And Mario Carnero, who's speaking later this week, he refactored modules for us. We got modules right second time, thanks to Mario. So what did we learn by just pushing the general idea that undergraduate mathematics should be formalized in one place? We learned that which parts were easy and which parts were hard, and we learned the pros and cons of various implementation decisions. And in my mind, these are really important things to learn about your theorem prover. If you're learning a theorem prover, you really want to know. You want to have a general overview of which bits of mathematics are going to be easy and which bits of mathematics are going to be hard in the logic that you've chosen to work in. So we learned a huge amount about this just by formalizing undergraduate mathematics. And as an added benefit, we've now got one library. And if the students use this one library, then they can suddenly do a vast, they can do their homework problems in many, many areas. They just have to import one library. Okay, so winding down now, Freek Wiedijk is explicitly, another speaker at this conference, he explicitly points out that a system that wants to formalize a substantial amount of mathematics, it needs to be somehow have, I'll just say what Freek said. We need to be able to integrate work by multiple people into a nice coherent whole. Different people interested in completely disjoint things. There's Sebastian Goertzl interested in manifolds, and there's me interested in algebra. We're interested in disjoint things. We're working in different areas in the library. And yet our work is being integrated into a coherent whole. And it's for two reasons. It's because of GitHub, which enables us to manage the library, and all of the continuous integration we're using with GitHub. We're constantly compiling various branches and making it easier for users. And the Zulip chat room, which is an extremely focused place where mathematicians and computer scientists can talk to each other about how to do various technical things in Lean. And these two things really, these pieces of infrastructure have been absolutely crucial to this general project of building a gigantic mathematics library. So how far have we got? This is pretty much the last thing I want to say. So I'd like to say we've done, I could say we've done pretty much all of Imperial's first year and 2/3 of the second year, and a third of the third year. But it would be nice to say more concrete things. And it turns out that Patrick Massot, who works in Orsay, as it used to be called, it turns out the undergraduate degree at his institution is extremely well specified. There's a very, very precise list of exactly what needs to be taught to the undergraduates. And so we went through this list very carefully, or Patrick did. And thanks to Patrick and the undergraduates that translated a lot of stuff into English, we can now take a detailed look. So I don't want to switch. I could stop streaming this and start streaming a web browser. There's a link here. If my notes end up public, you can click on this link, but I've got some screenshots here. I don't know how visible they'll be to you. But this is the screenshot of the page on the Lean Prover community website explaining what mathematics we have done. So you see, we have done, you just choose a random, you can choose a random area. You choose polynomial rings, and it says a bunch of things that I can barely read without. You see, these are the things we have done. We've done the polynomial rings are Euclidean domains. We've done Eisenstein's criterion. There's a bunch of things which are taught to students in Orsay that are now in the Lean Theorem Prover. And then you can also look at the parts of the polynomial rings that we haven't done. And there you can see there's some missing stuff, right? Cyclotomic polynomials, that's fun third year stuff. We teach it in the Galois theory course at Imperial. We're currently working on formalizing the Galois theory course. Several undergraduates and actually PhD students in UC Berkeley have got involved. So undergraduates at Imperial, PhD students at UC Berkeley, all in the maths department, are together formalizing Galois theory. So there's some and other random things. But if you go to these two websites, you'll see a lot is done and very little is, and a lot is done. And what isn't being done is often in the pipeline, which is really good to see. A lot of these things, when you look through them, you see it's not done, but there's people working on them. So it's not going to be long until we have an entire undergraduate mathematics degree. Give us another 2 years, say, and I suspect that we'll have an undergraduate mathematics degree in Lean. By which I mean we'll have a system which will be able to understand the theorem statements on the exams that we're setting our undergraduates at Imperial College, and it will also be able to understand the proofs if a human types them in. That's where we're going to be in a couple of years' time. And of course, typing them in is an entirely different matter. So last slide, it turns out that, you know, undergraduates are they're certainly not the most prolific contributors, and in some sense not the main contributors, but if you look at the top 20 contributors to Lean's maths library and order them by lines of code, I see 3 Imperial undergraduates: Kenny Lau and Chris Hughes, who I've mentioned before, and Amelia Livingston, who did all this refactoring of the localization of localization in. So mathematics undergraduates are becoming involved, and you see the undergraduate mathematics and the mathematics undergraduates, in my mind, are intrinsically linked. Many, many more Imperial undergraduates have contributed, some just a few lines of code, you know, and some just one directory. Like an Imperial undergraduate, Ellen Arlt, she defined matrices in Lean, for example. And I think that's her only contribution to Lean's maths library, but it was a contribution. You know, it's one I'm quite proud of. And so my idea basically is to keep telling young mathematicians about this software, because there's evidence that they're interested, certainly at my university. And if people start telling mathematicians at other universities, they'll get interested too. And the more and more, if young mathematicians start picking up on this stuff, then eventually there will just be some paradigm shift where all the researchers, you know, if they're not using this stuff, they will just be regarded as out of date. So that's what I'm going for, the paradigm shift. And there's me on Twitter. And there's my motto. But yeah, I'm basically trying to lead undergraduates astray. And that's all I have to say. Thank you very much for listening.
Thank you very much, Kevin. A big applause, actually, a virtual applause. It's not like the live experience, unfortunately. I see there already the first questions coming in, and while people might still think about theirs, I can already read the first one, I guess, I have here. This is from David Fuenmayor, who's also working a lot with systems like Isabel Hall and using sledgehammer tools in there, or the sledgehammer tool in there. And he's asking, to which extent do you actually employ in your work hammers in your formalization work? So I currently, and which future prospects do you see for using them?
So this is a very easy question to answer. I don't use hammers at all because I don't have access to them right now. There will be a hammer in Lean 4. We're doing all of this, we're making this stuff in Lean 3, and we've heard very optimistic noises from the developers of Lean 4 that much of it should go through smoothly to Lean 4, but there's a porting issue first. So once the porting issue has been solved, I mean, and independent of the porting issue, there's getting the hammer working. So this is something for the future in Lean, but of course in other systems like Koch and Isabel Hall, which I personally regard as 2 of the other really serious systems for mathematics. They have hammers already, but I don't see the community of mathematicians who are pushing to get an undergraduate degree into these systems. So we're looking forward to hammers, but at the minute we prove things by hand, and I quite enjoy that.
Right. So I would. Now I see many questions. Now
right.
I can just. Jack, you seem to have a question. You asked whether you.
Jack, I know from Twitter, but I don't think we've met in real life, or maybe we have.
I'm going to turn on my video so that you can see what I look like.
Are you Jack? I've seen your Twitter picture, right?
Oh, right.
Hi.
Right. So about publishing some of this stuff. So I'll reinterpret some of the things that you've discovered as discovering that the real structure, arrogantly call it the real structure of mathematics, is actually quite different from the structure of mathematics that we teach in undergraduate degrees. And what we teach in undergraduate degrees is very much driven by history.
Yes.
But it ought to be the case in an ideal world that once we discover, when we try to rebuild mathematics, what structure it actually wants to have, shouldn't this be publishable?
I think that Bourbaki discovered 75 years ago what structure mathematics should have, and they wrote a series of textbooks that were developing mathematics from first principles. These textbooks are not used for teaching, but I think Bourbaki already knows which order it should be in. Patrick.
Yeah, I think Bourbaki is wrong. I think by proving it formally, we've actually discovered that there's an even better order than Bourbaki.
Well, I don't really know how publication works in the computer science domain, but I think that my work on schemes could be publishable, and my work on perfectoid spaces was published, but these were both instances of formalizing things that hadn't been published before. I think that we are learning new things about what Lean is good at and what Lean is bad at. But on the other hand, I think that this might not be specific to undergraduate mathematics. We're just learning that because a lot of people are using Lean to do a bunch of stuff. I mean, there are papers published about Lean and its maths library. There'll be a talk about Lean's maths library at this conference, and there will be a publication. But I'm not sure that they'll be specifically focused on undergraduate mathematics. Yeah, this is behind. I think this is behind the scenes work for some reason, and it does have benefits, but the benefit to mathematicians is small currently, and the benefit to computer scientists is somehow the mathematics is abstracted away from that, and the computer scientists learn about ways of carrying around the data of a function that has a property, things like that. They learn about whether to bundle or to not bundle, and they learn things about ways of making it easier to use a large mathematics library because it's been growing incredibly quickly. It's 300,000 lines now, and it's growing at a quicker rate than ever before. So we've learned lots of things, but I'm not convinced that we've learned lots of things about undergraduate mathematics. I'm just not sure we're there. I think that Bourbaki knew most of what we knew. Nice to meet you, by the way. You'll have to explain to me on Twitter why that's not the case.
Yeah, we had, by the way, an excellent number here of participants, 135, just for your records. I saw the peak. So there's another technical question I have here from CW Lim. Maybe I read it, or do you want to?
No, I can see it, right? So yeah. CW Lim says he or she, they have a difficulty finding specific results to quote in the proof. And that's absolutely right. And a hammer might solve this quite well. But before that, we only have the tools which Scott Morrison has written. And Scott Morrison writes spectacular tools. He writes spectacular tactics. And the tactic that one has to use is library search, which if you feel that the result you want should surely be in Lean's maths library somewhere, but it's 300,000 lines of code and you don't know where to look, you can automate a search to try and find the result which will completely close your goal. So library search is a useful tactic. But if what you want is a combination of two theorems in Lean's maths library, but not actually in the maths library already, then you need to wait for the hammer, unfortunately. And the hammer isn't going to be here for like a year or so, but the hammer is coming. So you have to wait for the hammer.
Yeah, I also have a question later, but let's first, we have more here on the list. There's Yevgeny Makarov. Do you want to speak up yourself?
I'll happily talk to Yevgeny. Hi.
Yeah. Hi. Well, I was wondering about the difference in style in a textbook proof and a formalized proof. Suppose a student is reading and is missing some particular information, some transition from one idea to the next.
Right.
Is it possible to get it from a formalized proof?
The answer is sometimes. So the answer is, for the proofs I write, it's often the case that you can, because I tend to write very, very long proofs in Lean's tactic mode and put lots of comments in my code. Whereas in Lean's maths library, this is not the preferred style. The preferred style is to compactify your proof as much as possible so it compiles more quickly. And comments seem to be frowned upon. I'm not entirely sure if that's the formal policy, but comments seem to be frowned upon. So so if you're lucky and the proof that you want to try and understand is written out clearly and spelt out precisely, then you might be able to see what's going on. But if the proof is compacted, then it might be difficult. On the other hand, the compacted proofs tend to be the proofs that you see, that's not true. There are simple compacted proofs that say this trivial thing is true by a bunch of gobbledygook. And then the bunch of gobbledygook is you don't really care what it says anyway, because the result is obvious. But I've been reading through the proof of Sulov's theorems in Lean's Maths Library recently, because I've been refactoring them. And those proofs are really quite hard to follow if you have to be an expert. You have to learn how to follow them. You can read proofs, but you have to learn how to read them. I mean, you have to learn how to speak another language, basically. The proofs are written in a different language. It's as simple as that. But the information is there, although you have to learn techniques to get it out sometimes, is the answer. The information must be there somehow, but it's not always clear how to get it out.
There is, if I see that correct, I mean, there were comments from James, for instance, but the next question seems to be on my list from Michael Junk. I think you have to speak up because you didn't type it.
Yeah, hello.
Hi. Hi.
Yeah, thanks a lot for this very interesting talk.
Oh,
and
I
have a question. In fact, apart from having a big undergrad math library, which would of course be a nice thing to have, but is there also an immediate positive consequence as for the students doing it? I mean, do they get a much better insight into the true nature of mathematics? Do you observe anything like that? Or is it sort of covered up by lean specialities? Or do they really get, you know, what truth really means if you have a true formal language and all this stuff, which is in the informal style we usually teach our students? It's sort of not always, you know, they don't get the right picture of mathematics. Is that repaired in your approach?
Yes. This is a question I'm extremely excited to say that I've watched undergraduates learn Lean at a very early age as first years, and then they watch our mathematics degree and they start thinking about it in this more type theoretic manner. And as a consequence, they somehow think about it in a different way. And this is one of the most exciting things, really. I have MSc students who seem to understand what they've been doing in a completely different way to the way that people who are not engaged in Lean. They have, of course, a far more precise understanding of what exactly is going on. But also, they criticize their lecture notes because they see the lecturers proving the same theorem 3 times. They abstract more than the lecturers. They think we have this technique, this should be a sublemma. Why are we proving this sublemma? You know, in Lean you don't prove sublemmas, right? You pull the lemma out. It's very strange. We're teaching mathematicians to think in a new way. We're teaching undergraduates to think in a new way. Now, I don't know if that's important, but I do think it's interesting. I do think it's, and yes. So they're definitely, and they also know exactly when the wool is being pulled over their eyes. You know, they're sometimes given questions where a picture is drawn, you know, and they say, imagine trying to formalize this.
Yes.
But on the other hand, they know how to do it. They know it can be done, but they also know that something very strange is going on when they're given when they're giving a drawing of a torus and they're asked to do something with that drawing. So I should probably, I should flag Rob Lewis's comment.
Yeah, just an organizational comment. I let the discussion continue for a couple of more minutes, let's say quarter past maybe even, but we have to pay attention that eventually speakers for the next session need to prepare. That's unfortunate because I think we could now really have a longer discussion here. Questions are coming in, but we have the Slack environment as well, where we can eventually continue discussing afterwards and so on. So let's go for another couple of minutes, and we have here a question by Peter Köpke and then Robert Lewis as well.
Hi, Peter.
Hi, Peter. Yeah, Kevin, thank you very much for your talk. Very lean orientated. So my question, I can't read it anymore because it has gone away on the chat, but what about the other systems like MISA or Isabel, and they cover undergraduate mathematics. How much do they cover? Do they cover everything you are interested in? Is it good to sort of extract things out of MISA and Isabel libraries and say, let's look at that and formalize in those systems for undergraduates?
So sometimes we do this. Oh, I have this great echo. You're not using a micro. Ah, very good. So sometimes we do look at how things are done. Certainly, in particular in Isabel, we've certainly stolen ideas from them. At MISA, I've only ever glanced through what is there, but clearly there's a lot of undergraduate mathematics there. My worry about MISA is this closed source system that we can't upgrade in some sense. That's my main worry about MISA. And I wonder whether actually people learned a lot about formalizing mathematics in set theory from MISA. But in Lean, we've learned a lot about formalizing mathematics independent. In Lean, I think that all undergraduate mathematics should be formalized in all the systems, right? That's my personal take on this. I think that it's an extremely worthwhile and productive exercise because it forced us to do things that maybe computer scientists wouldn't have chosen to do because it's standard material. And then when you actually start doing it, you realize that there's more than one way of doing it, and perhaps some ways are better than others. So I think that it's an extremely useful, I think there's been a lot of benefits formalizing undergraduate mathematics in Lean. And maybe most of it is done in, the big problem is first and second year stuff, a lot of it is there. The problems start when you start doing manifolds, topological spaces with a lot of extra structure, because then the object isn't the topological space. The object is somehow the topological space and all the extra structure on top. I only learned recently that there was a lot of pushback about the formal definition of a manifold in the 1950s, because it seemed that it was a strange thing to have a mathematic, like a ring was a ring, it was a set and this structure. But somehow a manifold was a topological space with more stuff on it as well. It seemed, it was some kind of higher order construction. And I'm not aware of any sizable development of either the theory of smooth manifolds and differential forms in any system, but we're on the way in Lean. And also a basic theory of homological algebra and group cohomology and extant Tor groups in any other system. And these are taught to our undergraduates. So there are very actually specific parts of the undergraduate curriculum, which I think should be, one should attempt to formalize them in every system. And I'm almost will guarantee that they will teach you something about your system. Should students also use them? Mathematicians aren't going to push students to use these systems because you can't suddenly change everything from the ground up. It's kind of annoying. You know, I think that we do teach our students Python. Why shouldn't we teach our students Lean? Why shouldn't we make it compulsory, or one of these other systems? But it's going to be a hard job making that happen. You know, currently I'm working on getting a Lean course into our undergraduate curriculum, an optional third year course. I'm hoping that that will happen, you know, the year after next. I'm going to do a course for PhD students this year, and then there'll be a course for undergraduates next year once I've worked out what works and what doesn't work. So students should have the chance to use these systems, but I don't see why we should force them to do it. Some students aren't even interested in pure mathematics. So,
Rob, I think that's just a comment by you, right?
Sorry, what for me?
No, Robert Lewis.
Thank you, Kevin. Bye.
Yeah, cheers, Peter. I should let Rob speak. Go on, Rob. Undo all the damage I did.
No, I don't have anything to say except what I wrote in the comment that MathLib certainly does not discourage comments. In fact, we have a lot of infrastructure for incorporating comments and documentation, and there will even be a talk at this conference that partly covers this.
So I made a slightly cynical comment that there aren't that many comments in MathLib, which used to be extremely true, and now is becoming much less true, at least partially, I mean, mostly really as a result of Rob's efforts to start documenting the system. But individual proofs are often not documented, but we are slowly making documentations of each file in the library, you know, a module documentation at the top of each file. And these things are extremely important. In fact, this is at least partially an answer to the earlier question of C.W. Lim. If you know a bunch of, if you think that the result you want is in a certain file, then you can now start reading the module documentation for that file. The many I was very impressed with Coq always has this. Every Coq file you ever see has got 100 lines of comments at the beginning. Lean is going there. Stephen Obua.
Yeah, he's next on the list.
Yeah, I mean, the Lebesgue integral came first, which is kind of strange, but the Lebesgue integral is not what we're going to be teaching. Actually, I think when I was an undergraduate in Cambridge, I was told that in Oxford, they were teaching the Lebesgue integral to the first years. The problem with the Lebesgue integral is that you really need a theory of measure spaces first. You need an abstract algebraic object. And what do we teach? You know, what do we teach undergraduates? We teach them, the first years, we teach them two kinds of basic abstract algebraic objects, right? We teach them groups, and then we show them the Rubik's Cube. And we teach them vector spaces, and we show them we show them the classroom and say, this is R cubed. So these are two abstract algebraic concepts, but the idea is you're supposed to be able to relate them to the real world that we're living in. So we're not scared to teach them groups and vector spaces. But actually, when you look at the definition of a vector space, it's a huge list of axioms. I was quite surprised when I tried to understand it axiomatically. And we don't teach people monoids or semigroups, which are much conceptually simpler than groups. For some reason, we've just focused in on groups and vector spaces. So if you want to teach Lebesgue integrals, you're going to have to teach measure spaces. And maybe first-year undergraduates can't look around and see measure spaces. So maybe people are reluctant. I don't really understand teaching. Should we just teach people a bunch of abstract algebra? Yeah. Why, you know, group theory, abstract group theory and ring theory are kind of easy because the axioms are just there in front of you. Whereas analysis is incredibly difficult because the real numbers are a very rich and complicated object. So I'm a bit confused about why. I mean, it's just a historical fluke, I think, that we teach people the Riemann integral. But the Lebesgue integral needs more machinery. But on the other hand, it's much less fiddly. But you somehow need to know measure theory first. And measure theory is third-year stuff, right? That's, you know, that everybody knows it's third-year stuff. So of course you shouldn't teach it the first years.
I think we can only answer two more, probably the one here by Patrick and by Tobias. And then I guess we have to stop to give the other contributors later on a chance to set up their environment.
So
Patrick, do you want to speak up quickly, or?
I'm just reading it.
Yeah, reading it, and probably we try to speed.
Isn't it publication enough? Yeah, I think so. But then again, I've got tenure. What do I care? I've got tenure, so who needs publications? You know, and I'm working with undergraduates, and they don't need publications either. And this is why it's very easy for us to you know, it's very easy to start doing undergraduate mathematics. Yeah, I think, but you see, my serious professional colleagues, you know, when they're looking to hire people, they look at their CVs and they count how many papers. And you know, people that need promotions, they're under extreme pressure to publish. It's absolutely ridiculous. So there's this huge thing in the middle. This is why working with undergraduates is so much fun, because you say, oh, let's publish this at some point, and then nobody gets around to doing anything for a year, and nobody's having a nervous breakdown. Yeah, I think you're right. We're publishing it in a different kind of way.
Right, a new publication style, and when it becomes clear that the linchpin of some class of things is something that somebody formalized, that name will get out.
That's great, then that's fine. Then we are. I don't want to play by the system anymore. I'm sick of the system because I think that humans have done a lousy job. So I just want to do what's sensible now. And I think that formalizing undergraduate mathematics is just eminently sensible. You know, in all the systems. Tobias is talking about proofs in declarative stuff. I never quite know what these mean. If you can inspect the state, which I imagine you can in Isabel, if you can inspect the state at all points, then maybe these things, you see, they might be readable, but at the bottom line is they're written in a different language, and you have to learn the language. And in mathematics departments, because the staff are not using these systems. The staff don't know the language. So the courses which teach the language don't appear. And undergraduates look at these things and they see things like auto and sledgehammer, and they just look they look scary because no one is teaching them the language, right? That's something else I'm doing. I'm teaching undergraduates a new language. And I think, sure, once they've learned this language, you might well find that, that Isabel, if they know something about Lean, you might well find that they can read Isabel proofs. And
actually, but you don't have to teach them the language. Just tell them not to read the by auto. In fact, you can just elide that, and then it reads more like a math text. Because in a mathematics text, you wouldn't say 1 + 5 = 6 because, and then you would cite those axioms. But just let me be contrary. I think it's completely ridiculous to say write a proof and then comment it. If you have to comment your proof, then you're using the wrong language to write the proof in the first style. I mean, mathematicians don't write textbook proof and say, and then by magic this comes out. And now the
they do that. They do that. I mean, they do say, and the rest is obvious. But you see, it seems to me that what happens with Lean is that I've watched experts write Lean proofs, and they start off with comments, and then they write the proof in tactic mode, and then they start looking through it, and then they start deleting the comments, and then they tidy up the tactics because they realize they can do it in term mode. And then the proof gets shorter and shorter, so it compiles more and more quickly. And at the end of it, it's become a completely different thing. I encourage undergraduates to finish the proof and then stop, because I say if you finish the proof, you've beaten the level. But then there's this whole extra part to clearing the proof up, which I don't encourage. But the tidying up can make it much more unreadable. The tidying up can break readability quite spectacularly.
Well, I'm personally also a fan of ESA style proofs, have to say. And unfortunately, we can't continue the discussion here. So I invite you all to actually get your questions into Slack. I can also help to copy them over. I guess Kevin will also be available to answer some further questions there. We have to stop here to just have a short break for the others. And I think we should all give a virtual applause again to Kevin's presentation. It was a wonderful first invited talk here at CICM, and I really, big thank you to you.
Thanks for the invitation. It's always good to arrogantly push my own agenda. I'm going to stop recording now.
Yeah.